So sorry about that, got disconnected. But let's continue this next part of the video then with that last example that I'm going to set up here. All right, so here we have f of x equals 4x squared minus 16 over 2x minus 4. And what we want to do is we want to find the asymptotes of this rational function. If a question says to find the asymptotes, that means that's referring to find both the vertical and horizontal asymptotes. All right, so we want to first find the VA. Let's first find the VAs here, the vertical asymptote. And then we'll find the horizontal. All right, so recall for the vertical asymptotes, we want to take this function of 4x squared minus 16 over 2x minus 4, and then we want to see if we can simplify it. All right, so let's take out some common factors from the top and the bottom. On top, we have 4x squared minus 16. What do these two terms have in common? They have a common factor of 4. So we're going to have 4 on top over x squared minus 4. Divided by, now what do we have in common between the bottom two? 2x and negative 4 have a 2 in common. So 2 times parentheses, x minus 2. But we can still continue here, because what do we notice in the numerator? We have x squared minus 4. What is x squared minus 4? A difference of squares. All right, so here we're going to have 4 times parentheses, x minus 2 times x plus 2 all over, and what we're added here, I'll say for now, over 2 times x minus 2. Okay. So now, what do we notice? We have x minus 2 on top and the bottom. These two will cancel out, so we can cancel out that common factor. But what else do we see? We have a 4 and 2 in common here as well. So we can simplify that. So this 4 becomes 2, and this 2 just becomes 1. Leaving us with f of x equals, after simplifying, is going to equal just x plus, 2 times, you say, 2 times x plus 2, because we still have a 2 outside the top here. In other words, 2x plus 4. Meaning, do we have a denominator left? No, we have no denominator, which means this function has no vertical asymptotes, because all we found for this rational function, so we're able to cancel that x minus 2, all we found was a hole in our function. So we have a hole at x equals 2, but no vertical asymptote. All right. So now let's try to find the horizontal asymptotes, the HA. All right, so again, to find the horizontal asymptotes, we want to take the limit as x goes to infinity for this function that we have above here of 4x squared minus 16 over 2x minus 4. And again, to find your horizontal asymptotes, divide each term by the highest power of x in the denominator, which in this case is just x. So we divide top and bottom by x, not 2x, just a variable. Okay, put a different color. All right, so divide top and bottom by just x. All right, so you're going to have the limit as x goes to infinity of 4x squared over x minus 16 over x all over 2x over x minus 4 over x. Okay, so simplify what we can. This x squared and this x on the bottom, we can factor out one, we can cancel out one factor of x, so this becomes x to the first, it just becomes 1 on the bottom. 16 over x just remains the same, and then 2x over x is canceled out here. So now we have the limit as x goes to infinity of 4x minus 16 over x over 2 minus 4 over x. Okay. Now what's going to happen here? Oops, got limited. So now we don't want to take the limit of each individual term. Again, like we have seen before, the limit of a constant over a changing variable as that variable goes to infinity, 16 over x is just going to become 0. It's going to have 1 minus 0. Limit of a constant is just that constant. So we're going to have 2 minus, again, the limit of a constant over a changing variable as that variable goes to infinity. That will also be 0 here. But what about the limit of 4 times x as x goes to infinity? What happens to 4x here as x keeps getting bigger and bigger? Where x gets larger and larger and larger, 4x will also get larger and larger and larger. In other words, the limit of 4x, x goes to infinity, is going to be infinity. So we're left with infinity over 2. And infinity divided by 2 is just infinity. Meaning, is the function going to reach a limit as x goes to infinity? No, there is no limit. Meaning that for this function, we also have no horizontal asymptote. Okay, so this rational function of 4x squared minus 16 over 2x minus 4 has neither a vertical nor a horizontal asymptote. Okay. What we found for this function is a hole at x equals 2. All right. So now that we have done this algebra review here of asymptotes, let's now do some examples of relative extrema for these rational functions. Okay. So let's see. Let's do 2 examples here. 2 or 3 maybe. 2 should be good. All right. So let's start with one example here. Let's actually do one that we earlier, that we already done before. All right, let's find the relative extrema of an earlier example that we did, whose asymptotes we already found. Let's find the relative extrema here of f of x, where f of x is 3x plus 6 over x minus 2. All right. Again, we have done this one before. Recall, for this function, we found its vertical asymptote, which is located at x equals 2. And for this function, we found a horizontal asymptote at y equals 3. Okay, so just put this a reminder. For this function, we find a vertical asymptote at x equals 2. And then we find a horizontal asymptote at y equals 3. And I'll rewrite that. Okay. So, but in this case, we want to find the relative extrema, meaning the relative min or max. And how do we do that? By first finding its derivative. So let's find f prime of x first, the derivative of our function. Okay. And how do we find the derivative when we have a function of x being divided by another function of x? Got to apply that quotient rule. All right, so you're gonna have, I'm already using f, so let me use h and g. So h of x will be our top function, which in this case is 3x plus 6. G of x will be our bottom function, which in our case is x minus 2. Find the respective derivative, so h prime of x equals 3, and g prime of x, it's just gonna be 1 here. All right. And now it's time to apply that quotient rule. So let me bring this down here. So again, we want to find f prime. We have to find the derivative of this rational function. We first got to take h prime, the derivative on the top, which is h prime, 3 times our original function at the bottom, g, which is x minus 2, minus h here, which is 3x plus 6, times g prime, which was just 1, all over g squared, all over x minus 2 squared. Okay, so now let's distribute and combine like terms on top. So let's see, on top we're going to have 3x minus 6 minus 3x minus 6 all over x minus 2 squared. Okay, and combine the like terms on top. What do we notice happens here? The 3x's are going to cancel out. 3x minus 3x cancels out, leaving us with negative 6 minus 6, which would be negative 12 over x minus 2 squared. All right, so that's our first derivative for this rational function. Okay. So now, second step, recall. After we find the first derivative, then the second step is to find the critical numbers. And we find the critical numbers by figuring out which values of x will make our first derivative 0, or make that first derivative undefined. Okay. So again, our first derivative here is 12 or negative 12 or x minus 2 squared. So we want to figure out what values of x. Let me write this. We either make the function 0 or undefined. Okay. Now, to figure out what makes it 0, we got to look at the numerator. But do we have any x in the numerator? No. So in this case, we don't have to worry about the numerator. And now focus on what makes it undefined. And what makes it rational undefined is what makes the denominator 0. So in this case, we do have a variable x in the denominator. So what we do now is take our denominator here of x minus 2 squared and set that equal to 0 to figure out where it will be undefined. Okay, because if the denominator is 0, the first derivative will not be defined. All right, so x minus 2 squared, well, we can just use the rules of algebra, square root both sides. Square root of 0 is just 0. So square root both sides gives us x minus 2 equals 0. Solve for x, it gives x equals 2. So here we have found a critical number at x equal 2. And notice this critical number at x equals 2 was also our vertical asymptote at x equals 2. Okay. Again, a vertical asymptote represents a break in your function. And when there's a break, that means the slope at that point is not defined. Okay. So if our critical number then is the same as our vertical asymptote, then what's going to happen when we find a relative extrema here? So now the third step, that first derivative test. What's going to happen here? Well, let's follow the steps again of the first derivative test. So we call for the first derivative test, draw a number line. First draw our critical numbers, which in this case was just 2, so just one critical number. And in this case, if we were to plug in this critical number into our first derivative, it's going to make it undefined, not 0, undefined, because we got the solution from the denominator of our derivative. All right, if we plug in 2 into this first derivative, it makes the denominator 0, which makes the function undefined. Okay, And just like we have done before, pick a test point before and after our critical number. So let's pick any test number. I'll just do 0 and then 3 here. And again, we take these test points and plug them to the first derivative. All right, so plugging in 0 into this function here, negative 12 divided by 0 minus 2 squared. That's going to give us negative 12 divided by 4, which is just negative 3. Okay. And then plugging in 3 to our first derivative, so it's going to give us negative 12, or 3 minus 2 squared. 3 minus 2 is 1. 1 squared is just 1. So negative 12 divided by 1 to give us negative 12. Meaning that before this first critical number, since our slope is negative based on that test point, that means our function is decreasing. But then it hits this undefined area. In other words, hits that vertical asymptote, hits that jump in our function. And after that jump, after that critical number, after the jump to this critical number, the slope is still negative, which means it's still decreasing. So it's negative before the critical number, before this jump, and then negative once again. Which means then what? If there's no change in the sign of our direction, if there's no change in the sign of the slope, then that means we have no relative extrema at x equals 2. So here we have no relative max nor min. So no relative max nor min. All right. Again, let's look at this graph. We did a little sketch of that graph earlier. Again, here we have the critical number, x equals 2. And as we go towards that critical number, our function is coming down, it is decreasing. Then we make a jump, and after that critical number, as we go to the right-hand side, it is still decreasing. In this case, decreasing towards y equals 3 at this horizontal asymptote. So there's no change in this direction of the curve of this function before and after that critical number, which means we have no relative max nor min, no relative extreme